Welcome. In this video I'm going to show you how you can analyze a single binary variable using the stikpetR library and of course therefore R. I'll leave a link in the description below to this Jupyter notebook because I'm using Jupyter notebook, but the code should just work exactly the same in R or RStudio. The links in this notebook are actually each time to the documentation for my Python version of this library, but that should be just about the same. To analyze a single binary variable, what we're going to do is we're going to create a frequency table. We then use a one sample binomial test, and last but not least determine coin G as an effect size measure. There are some alternatives. I won't go into too much details on this. This is just a quick introduction on how you could analyze something like this. My library isn't available on CRAN, so in order to install it you will need to install it over GitHub. You can use, you will need DevTools for that, and then you can run this. I have of course already done that, so I'm just going to load my library in. And of course I'll need an example. So my example data is also available on my website, so I can just download it from there. And we need only one field of that, and I'm going to be using the gender. In this case people only opted for male or female, so I'm also going to code those as male and female. Then, to get a quick impression, we can simply use the tab frequency function from the stikpetR library, and as you might see, here are the frequencies, the percentages, the valid percentages, and the cumulative percentages. In R you won't see this, which is I think better. That's the data type that's actually in that column. Now you might notice a small difference between percent and valid percent, and that indicates that there were some missing values. Now in this case it seems that about 74% were male, so we might be curious if that's a significantly more than the number of females, so if that's a significantly higher percentage. We can use the binomial test for that, so TS binomial OS. We simply give it the data and our two codes that it needs to be using, and that gives us the result, a p-value, and the test that was actually used. P-value is below 0.05, which usually is an indication that therefore there is a significant result. In this case we tested that it would be 50% in the population, so it's significantly different from 50-50. Of course, with any test we should also include an effect size measure. For that we could use coens G. It's available under ES coen G, and then again the data and the coding that was used. In this case it's about 0.24, and as a rule of thumb you can actually use the TH coen G. At the moment I think there's only the Cohen's rules of thumb for this one. Perhaps in the future I'll add more. And finally we therefore can classify this as a medium effect size. So overall we could then report it something like this. Now it could be that your data is not text, but it's actually converted to numbers. So for example I've done that in a different file which has 1, 2, 3 indicating that it was in numbers. It's exactly the same, but now everything is numbers. So I have a coding now as a somewhat as a dictionary where female is 1 and male is 2, but the numbers itself are simply 1s and 2s. So I can exactly use the exact same functions now, but use my coding D, and as you can see it's the exact same result. Of course the exact same result, and again the exact same result. There are some alternatives, alternative tests if you will. You could perform a score or a wall test, and these will actually give you the same result for the textual data and the numerical data as well. As you can see, this is actually using a normal distribution, so that's why you get a statistic there, and the p-value. And if you do the wall test, slightly different than the score test. As you can see the results are slightly different, but for the text and numeric data the results are of course still the same. Alternative effect sizes could be coens H for one sample. There's a function for that of course in the library. And also for the numeric it gives the same result. We can ignore the negative sign actually for coen H, so that's why these are exactly the same. We could convert this to a regular Cohen H using the ES-convert, and the reason why we might want to do that is because then we can use Cohen's H rules of thumb, and that in this case will still classify it as medium. There's also something known as an alternative ratio available as a function, of course, and both produce the same result, or should produce the same result. There's a difference here. All right, I'll fix that. Last but not least, the Rosenthal correlation coefficient, and that's about it. That's a effect size measure or correlation coefficient that you could use if you've used that score or wall test. Alright, of course each of these functions has more details. You can always just run a question mark and then the name of the function. So for example on that alternative ratio I could just do this and it nicely gives me the result. As you might notice, my functions or my equations are not showing up nicely here, so if you go to the website where the function links to, then it will show up nicely. Alright, hope this was helpful and thank you for watching.